Hello, and welcome to the last note video for college statistics. Not saying last video, but last note video. So this is the last new material that I'm going to be presenting. Pretty exciting. Alright, so what we're working with today is the chi-square distribution, so same as last time. Only we're going to be looking at situations where we have more than one variable. Alright, so last time when we did the chi-squared goodness of fit test, there was only ever a single variable. Alright, when we do our test today, we're going to see that there's multiple variables. Alright, so that's going to be the big difference. Instead of basically working with a single row of data, we're going to be working with a table of data. So, the name of the test that we're going to start with is the chi-squared test of homogeneity. And this is a test comparing the distribution of counts for two or more groups on the same categorical variable. Alright, so let's take a look at this first example here, and then I'll tie it back to the definition. So, does background music influence wine purchase? So basically the music that they're playing in the store, does that influence what people are going to buy? So market researchers know that background music can influence the mood and purchasing behavior of customers. That's true. That's why the music that you hear in stores is usually chosen for a specific reason. One study in a supermarket in Northern Ireland compared 3 treatments: no music, French accordion music, and Italian string music. Under each condition, the researchers recorded the number of bottles of French, Italian, and other wine purchased. Here is a table that summarizes that data. So, again, we're comparing the distribution of what was sold for each of the different groups that we created. So we created a no music group, we created a French music group, and we created an Italian music group. Those were the 3 groups we created as the researcher. And then after we created those groups, we're checking, does the distribution of wine type change? All right. So again, we're kind of working in this table environment instead of a single row environment. All right. Now the other thing that I'm going to put up here, and this is going to make more sense in a little bit when we get to the second test, but I'm going to put a little star here and say that when we're using this test, you generally have multiple samples. So for example, in our little question down below, we have a no music sample, we have a French music sample, we have an Italian music sample. But those are conditions we created. We created the no music condition and then surveyed what happened there. We created the French music condition, surveyed what happened there. We created the Italian music condition and then surveyed what happened there. All right, so when we're using this test, there's usually going to be multiple samples that we've created or multiple groups that we've created. All right, that's another way we could think of it. Instead of samples, we could think of groups that we, the researchers, have created. And then we're going to use those to kind of analyze what's going on. All right. So, as usual, anytime we're doing a test, there are conditions that are in place. So, very similar to the conditions from last video, there's the categorical condition. This test doesn't work for quantitative data. But with that said, you can put numbers into categories. So, for example, you wouldn't be able to use it just straight on people's ages, all right? That's a quantitative variable. But if you created categories like, oh, here's the 20 to 25 category, and here's the 25 to 30 category, and the 30 to 35 category, and you place that data into categories, all right, that changes it from quantitative to categorical, and then you would be able to use this sort of test. Randomization, I think at this point we should be pretty familiar with that. That's always a condition for everything. 10% is the same 10% we've been doing all along. It's got to be less than 10% of the population. All right, and that's, again, if sampling without replacement. All right, we've seen situations where things are truly independent, and then this doesn't actually matter, like when you're flipping coins or rolling dice or something like that, without replacement. And then, similar to last video, we have an expected cell count of at least 5. So I just want to emphasize this is expected. So the expected value in each box of our table needs to be 5, not the actual values. So you can have an actual value below 5 and be fine, as long as the expected values are all 5 or greater. All right. So again, very similar to the conditions we've been seeing for the last 2 months. Very similar to the situations that we were seeing just yesterday, or just last video. So, how do we write a hypothesis for our chi-squared test of homogeneity? They're generally going to be pretty much always the same. All right, you're just going to be subbing in a few words here and there. But the null is, again, the statement of no difference. So the way we write that for this is the distribution of wine type sold is the same across all music environments. All right, so we list first that which we're actually measuring, so the wine type, and we list second the groups that we created. So we created the music environments, we're measuring the wine type sold, so we write the null hypothesis as the distribution of wine type sold is the same across all music environments. And then the alternative is just pretty much the same exact sentence, only you're going to use is not instead of is. So the most annoying part about these problems is just writing the nulls in the alternative, because they're pretty much exactly the same with just 1 or 2 word differences. Of wine type sold is not. So that's really the only difference. The same across all music environments. All right, so if you think just back to the word homogeneous, all right, from like your science class, homogeneous is when everything is kind of like mixed together and the same. So our null is that basically each group is the same. It has no impact on our other variable. So in this case, purchasing habits is totally unaffected by the type of music being played. And then the alternative is that it's not the same, that this music would have an impact. It would change the distribution of wine type sold. All right, so that's kind of what we're testing here with this chi-square test of homogeneity. We're seeing, is the distribution the same across all of our groups? And again, I'm going to put same in quotes. It doesn't have to be exactly the same, but is it close enough that we say it's effectively the same? Or do the different groups seem to have an influence? Do the different groups change what would be expected from the other variable? All right, so that's kind of the general idea of what we're looking at here. So as usual, we're going to kind of walk through how this would actually work, and then I'll show you how it's going to play out when we actually use our calculator and technology to do it. So step one is we're going to need a chi-squared statistic. All right, now to get a chi-squared statistic, we're going to need expected values. So we're going to start by computing the expected cell counts. All right, and the way we get the expected cell counts, all right, so the expected count equals the row total times the column total, all divided by n, which you can just think of as the table total. So the entire sample that you're dealing with. All right. So let's look at how this would sort of play out. So here are our observations. All right, this is what we actually observed. And then down here, we're going to fill in what should be expected. Now, the way you can kind of think of this is here we have all the French wine that was sold. 30 bottles sold when no music were playing, 39 when French music was playing, 30 when Italian music was playing, for a total of 99 bottles. So that's our row total. All right. Altogether, in our little experiment, there were 243 bottles sold. So if I did 99 over 243, all right, this would give me the percent of French wine. All right, so if I do 99 divided by 243, let's just see what that works out to be really quickly on the calculator. 99 divided by 243. All right, so roughly 41% of the wine sold was French wine. So if I'm saying that music doesn't matter, then what I'm going to do is I'm going to say, all right, there were 84 bottles sold of all types of wine when no music was playing. And if French wine usually represents 41% of the wine that's sold, I want to know what 41% of 84 is, because that's how much French wine I should expect to be sold when no music is being played. So again, what I did is I found the percentage of wine that was French wine. All right, it was about 41%. I said, all right, there was 84 bottles of wine sold with no music, so what's 41% of 84? Again, that's my row total, my column total, and it's all being divided by the table total. So that's where these expected counts are coming from. All right, so this is the sample size for no music. All right, and this works out to be something like 34.22. All right, and that 34.22 would go right in this box right here. All right. Now, what I would do is I would then repeat that process over and over and over and over again. So I would say, all right, for this box, it would be 99 over 243, but I'd multiply it by the 75. For this box, it would be the 99 over 243, but I'd multiply it by the 84 box. All right. When I got down to the Italian row, I'd have to say, all right, Italian was 31 out of 243. Now let's multiply that by the 84. All right, Italian was 31 out of 243. Let me multiply that by the 75. Italian was the 19 out of the 240. Sorry, Italian was still 31 out of 243, but now let's multiply that by the 84. So just continuing to go through the boxes one after another and filling them in. So you can see that it's a little tedious to do this. So what I'm going to do is I'm just going to fill in the numbers here because we're really not going to do this by hand very often. And by very often, I'm never actually going to ask you to do it by hand. We're always going to use technology to do it because, again, it's one of those things that's just super tedious. We're more likely to make a mistake than a computer is. So now that you've seen where these numbers are coming from, let's let the computer do it because it's going to do a better job than we are anyways. All right. So there are expected values. They should total up to exactly what the original totals were, plus or minus possibly a little rounding error. So I'm just going to write in those original ones. But if you were actually doing this out, it's a nice check because you can add up those numbers and make sure that you're getting the totals that you should be getting. And if you're not, then you probably goofed something up along the way. All right. So once you have all of those values in there, all right, now we're ready to calculate our chi-squared statistic. And the chi-squared statistic works exactly the same way as it did in our last video, only instead of doing it for just one row, we do it for the entire table. So our chi-squared statistic equals the sum, and I'm going to write cells under here, for we're adding up the entire table, so maybe I'll just write that too, entire table. All right, and what we're doing is observed minus expected squared, the same as we did last class, divided by expected. So all of that is exactly the same as it was last class. So for each box, we would do 30 minus 34.22, square that, divide by 34.22. Then we'd go to the next box and say 39 minus 30.56, square that, divide by 30.56. So on and so forth, over and over and over again. Add up all of those numbers, and that would be our final kind of chi-squared statistic. All right, and for this one, it works out to be 18.27 when you do all that. But again, you can see how tedious that would be to actually do it by hand. So most often, we're not going to. All right, now once you have your statistic, we have to see where that falls in terms of our chi-squared distribution. And remember from the notes from last class, all right, the shape of this distribution changes quite a bit based on how many degrees of freedom you have. Now, last time, the degrees of freedom were one less than the number of categories. When you're doing a table, the way that it works is it's the number of rows minus 1 times the number of columns minus 1. All right. And what I'm going to put under this is ignore the total column / row. All right. So if we look at our example here, All right, ignoring the total column, we have 1, 2, 3 rows. We have 1, 2, 3 columns. So for us, it would be 3 minus 1 times 3 minus 1, which is going to give us 4 degrees of freedom. All right. Once you know the degrees of freedom, then it's just a question of putting it into the chi-squared distribution. So again, when we're doing it out the long way, that means going to the distribution menu. You go down to chi-squared CDF, just like we normally go to NCDF. All right. The lower bound is your chi-squared statistic. So for us, that was 18.27. The upper bound is basically just always going to be 9999, because again, remember, this distribution bottoms out at 0. There is no negative 999 here. So we're generally always going up. And then our degrees of freedom, we already calculated to be 4. So if we click paste and hit enter, we'll get our value there. All right, so really quick, let's just write out that this was chi-squared CDF. We put in 18.27 as our lower bound. We put in 9999 as our upper bound. And we had 4 degrees of freedom. And this gave us a p-value of 0.00, and then when we round, let's say 0011. All right, so this was 0.0011. All right, that represents our p-value. So same as it's been for the last, month and a half, 2 months, based on this p-value, we can say because our p-value is under 5%, we reject the null and accept the alternative. And again, just to put this in the context of the problem, all right, what that implies is that music changes purchasing habits. All right. If we had failed to reject it, then there wouldn't have been enough evidence that people really changed their behavior based on the type of music. But since we rejected it, we said there's enough evidence here to show that the distributions have changed as the music type changes. So it's not consistent across the board. We are seeing a change here based on the music that was playing. People are purchasing different things. All right, so here's the good news. As tedious as it is to do one of these by hand, it's actually incredibly easy to do them on the calculator. So it says, how can you do the test on the calculator? There's really only 2 steps. All right, step 1 is you enter the actual data. So not the expected. We're not going to have to calculate the expected. The calculator will do that for us. So enter the actual data into matrix A. If you've never used the matrix before, I'm going to show you that in a second. And then step 2 is run the chi-squared test. Right? And that's really all you have to do. All right, so it's really, really easy. So if you've never used the matrix before, it's the 4th key down, and it's the second function. So it's the second function of x to the negative first. So if we go second x to the negative first, that brings up the matrix menu. All right, there's names, there's math, and there's edit. To enter a matrix, you go into edit. At the top, it gives you the dimensions. So the first number is the number of rows. So let's say I wanted 5 rows. The second number is the number of columns. So let's say I wanted 4 columns. It would create that matrix for me. And then I would just go through and scroll through and type in the numbers, basically matching my table. All right. Again, you wouldn't enter the total columns or the total rows, just the actual data. All right. So not the totals for either the rows or the columns. So just to kind of show you how this works, if we go back to our example here, we had 3 rows and 3 columns. All right. So that would be 3 by 3. All right, and then I already have the data typed in here. So 30, 39, 30, 11, 1, 19, so on and so forth. All right, so once it's in there, you go to Stat, you go to Tests, same place we've been going. We're not using the goodness of fit test, we're just using the regular chi-squared test. It wants to know the matrix where you put your observed data, so we're usually just going to put it in A, so the default is fine there. And then expected, it's not asking where the expected is, it's asking where do you want us to put the expected matrix. So when it runs this, it's going to create those expected values and it's going to place them in matrix B. All right, so again, that's not saying that you have to put them in there, you just have to tell where you want them to go. And then you hit calculate and it spits everything out for you. All right, so 18.27 is what we got here. All right, our p-value of 0.00108 is what we got here after you rounded everything. So degrees of freedom 4, that matches what we said it would be. So really, really easy. And then if we go to matrix B, all right, and we go to edit, and we go to matrix B, you're going to see that it put all those expected values in there for us. All right, so the 34.2, the 30.56, 34.22, and so on and so forth. So it does all of that for you, and it makes carrying out these problems actually pretty easy. The calculator will do kind of most of the heavy lifting for you, because again, doing these by hand is just incredibly, incredibly tedious. So, you know, we're just not going to do that. All right, so let's take a look at some problems here just to make sure that we've got everything sort of squared away. So, how are schools doing? The nonprofit group Public Agenda conducted telephone interviews with 3 randomly selected groups of parents of high school children. There were 202 black parents, 202 Hispanic parents, and that's actually a typo. The table is correct. There were 212 white parents. One question asked was, are the high schools in your state doing an excellent, good, fair, or poor job, or don't you know enough to say? Is there evidence that the parent groups responded differently? All right, so first things first, just notice that there are multiple groups that we selected. All right, so we created these 3 groups. And again, it's going to be, you're going to see in a little bit why I keep pointing this out, but just recognize here that there are multiple groups. All right, and then we're seeing, does the opinion about schools change based on the group that you're a part of, or does the group not matter? Are opinions consistent across all 3 groups? So again, the process is going to be very similar to what we've been doing. We're going to start with our null hypothesis. And we could say the distribution of school opinions is the same across all groups. And then our alternative is pretty much the same exact thing. Only instead of saying is the same, we say is not the same. All right, so that's really the only difference between these 2 sentences across all groups. All right. We still pick an alpha level. That hasn't changed. So our alpha level would still be 0.05. All right, same as it's always been. And then at this point, you're really just sort of putting it into the calculator. All right, so we go here. We're going to go to our matrix menu, which is second x to the negative 1. We're going to be editing matrix A. Again, the first number is the number of rows. So in our table here, we have 1, 2, 3, 4, 5 rows, because again, we don't use the total right there. All right, so we have 5 rows. And then we have 3 columns. So that gives us the appropriate matrix. And then we just go through and we type all of those in. All right, 34, 33, 69, 55, 81, 75, 61, 60, 24, 24, 24, 22, 28, and 14. All right, so you just go and type all of those numbers into the table. All right. Then you go to Stat, Tests, chi-squared test. All right. Observed is where we just typed it. Expected is where we're going to put it, and the calculator will automatically change the size to be whatever it needs to be. You don't have to go in and make sure that B has the right size. It takes care of all of that for you automatically. All right. So then really all you have to do is hit enter. You're going to get your chi-squared statistic. You're going to get your p-value, and then they list the degrees of freedom. So really quick, degrees of freedom, according to our calculator, was 8. And just remember, that's coming from the number of rows minus 1, so 5 minus 1, which is 4, and the number of columns minus 1, which is 2, which is where the 8 is coming from. All right. But other than that, we just kind of want to write down our different results here. So our chi-squared statistic is 23.19. Chi-squared statistic is 23.19. And then again, when we compare that to the chi-squared distribution and see how much area is above that value, that's where our p-value comes from. And that's 0.003. So that's below 5%. So our conclusion would be we reject the null and accept the alternative because our p-value is under 5%. And again, just in terms of real world significance, what that's saying is it's saying the different groups have different opinions on schools. All right. Now, you as the statistician, it would be your job to then go through here, calculate some percentages, see what those differences are and what they mean. This is just saying that, hey, there's enough variation in these results that the different groups seem to have different opinions. All right. It's not like they're close enough that we can basically say, yeah, all 3 groups basically have the same opinions. This test tells us that all 3 groups don't have the same opinions. And then it's your job to go through and analyze that a little closer to see why that might be or what those differences actually are. All right, that's kind of how that works. All right, so let's take a look at another one. Smoking. The Gallup Poll Monthly reported on a survey built around the question, what is your opinion regarding smoking in public places? They conducted random samples in 4 areas of the country. So again, I'm going to underline this and emphasize that it is multiple samples. All right. On the workplace part of the survey, respondents were asked to make one of three choices as to the policy they focused on smoking. The policy they favored on smoking in the workplace. Is there evidence to suggest that opinions about smoking policies are not the same across the 4 regions of the country? So one thing to notice about this table is that they're giving you percentages. So they're saying 65%, 31%, 4%, 61, 36, 3%. When you're doing the chi-squared test, you can't use percentages. You have to use the actual counts. So what that means is you have to go through and convert each of these to what they'd actually be in terms of counts. So 65% of the 246 that were in the East, all right, and again, you kind of have to pay attention, but you can see pretty clearly that like these percentages are going across because these are the ones that add up to 100%. These add up to 100, add up to 100, add up to 100. Pretty clearly, they don't add up to 100 going down. So we are going across here. Also, we have these numbers. We don't have any numbers down here, so we wouldn't really be able to do that anyways. But 65% times 246 gives us 159.9, and we're just going to round that to 160. And then you would go through and do that same sort of thing for all of the cells in the table. So 31 times 246, and you'd end up with 76. And then 4% times 246, and you'd end up with 10. All right, and then you would just repeat that over and over and over again. But just be aware that if the problem gives you percentages, you have to switch them over to counts to actually be able to use the chi-squared test on your calculator. You can't just put the percentages in the matrix. That won't work. You need to be putting the actual counts in. So I'm not going to walk you through multiplying each of these. I'm going to trust that you can multiply a percent and a number. So let's just fill these in. 208, 119, 76 we already did, 92, 83, 72, 8, 15, and 8. All right. So again, just something that you have to do if they give you percents. You have to do that one little extra step of converting them over to numbers. But once you've converted them over to numbers, it's exactly the same problem we just did. So you've got your null hypothesis, and this time we're still dealing with opinions, so we could say the distribution of opinions on smoking, because again, smoking is what we asked about, and then these are the groups that we created. So what we asked about comes first, the groups we created comes second. So the distribution of opinions on smoking is the same across all regions, and then the alternative, again, is exactly the same thing. Only we're replacing is the same with is not the same. All right, so again, this is the most tedious part of these problems of opinions on smoking. On the bright side, if you're doing these on the computer, which you probably will be, you can just copy and paste the sentence, and then you don't have to type it twice. So that's good for you, bad for me doing these videos. All right, so we've got those down. We still need our alpha, same as we always do, and we're just going to keep that at 5%. We have no reason to do anything else. And then it's just a question of going in and putting that data into your calculator. All right, so second x to the negative 1 is the matrix menu. We go to edit. Again, the first number is the number of rows, so this time we have 4 rows and 3 columns. All right. Again, I'm leaving out this sample size column. I needed that to calculate these, but I don't actually put this into my matrix. So I've got 160, 76, 10, 156, 92, 8, 208, 83, 15, 119, 72, and 8. All right, so got those all in there. It's always good to just do a quick check to make sure you didn't goof anything up. But once you've got them in there, it's just stat, tests, chi-squared test, not goodness of fit. That was last video, so just the regular chi-squared test. Observed A, expected B. There's no reason to really ever change those. You hit calculate, and there's your results. All right. So again, degrees of freedom, just to make sure that we know where that's coming from. So degrees of freedom, they told us were 6. And again, that's 4 minus 1, which is 3, times 3 minus 1, which is 2. 3 times 2 is 6. So that's where that value is coming from. Our chi-squared statistic that it gave us was 7.49. The p-value, by finding the area above that number on the chi-squared distribution, is 0.2782. And then based on that p-value, we can write our conclusion. So let's see here. Because our p-value is over 5%, we fail to reject the null. All right. Which, again, sort of the real world implication of that is there's not enough evidence to show regions make a difference on smoking opinions. So basically, it doesn't matter what part of the country you go to, there are pretty similar opinions on smoking. Or at least, we didn't find enough evidence to show that the opinions were substantially different. Now you can see that they're not the same. All right? We never said they were exactly the same, but we're saying that those are close enough to be sort of within the realm of statistical variation that we're not going to worry about any differences that might have popped up there. All right, so that's kind of the implication there is, yeah, they're not exactly the same, but we're okay with that. All right, they don't need to be exactly the same. As long as they're close, we're willing to say, all right, you know, this is fine, this is good enough. Okay. All right, so that brings us to the final page. All right. So the final page is the chi-squared test of independence. And here's the great news. It functions exactly the same as the chi-squared test for homogeneity. We're not doing anything different. The process is exactly the same. The difference is how we collect our data. And depending on how we collect our data, we're either running a test for homogeneity or we're running a test for independence. All right, and that's why I kept underlining that it was like multiple samples. This is going to be from a single sample. So let's just put a definition in here. A test of whether two categorical variables are independent. And then we're just going to put a little note here that says calculations are the same as the test for homogeneity. And then we're also going to make a little note up here that when we're doing these are coming from a single sample. Now, you might recall that earlier in the year when we were doing like probability, we had a test for independence. And it was if the probability of A equals the probability of A given B, we said two things were independent. But we said they had to be exactly equal. I mean, when you're dealing with the laws of probability, or the rules of probability, A has to equal A given B. But when you're gathering data in the real world, you know, it might not always be exactly the same, but if they're close enough, we can kind of say that two things are independent, or we can at least say we don't have enough evidence to say that they're not. So that's what this test is going to allow us to do. It's basically going to allow us to test for independence without having the strict A equals A given B rule. All right, it's going to give us a little more flexibility in kind of how we do things. All right, just note that this is going to work exactly the same as what we've been doing. The only difference is going to be how we write our null and our alternative hypothesis. Everything else is going to be exactly the same. Let's take a look at this problem here and kind of see how this one is different than the ones we've previously been doing. So, smoking students and parents. Are the smoking habits of students related to the parents' smoking habits? Here are the data from a survey of students in 8 Arizona high schools. Now, you might be saying to yourself, 8 high schools, that's multiple samples, right? Here's why this one is different. All right? We didn't divide up the students. We didn't go out and search for students who smoke and survey them, and students who don't smoke and survey them. All right? We didn't go out and search for students who had parents that smoke. We didn't go out and search for students that had one parent that smokes. We didn't go out and search for students that had neither parents that smokes. All we did is we gathered a whole bunch of students and asked them 2 questions. All right? We didn't divide them up. All right? If we look back at some of the previous ones that we've just done, all right, on this one, we divided them up into region and went to the east and did a separate sample, went to the Midwest, did a separate sample, went to the south, went to the west, and did separate samples and only really asked a single question. You know, here we went and surveyed 3 different groups, but really only asked a single question. Going back to the very first thing we did with the music, all right? We set up the different music and then really only surveyed the buying habits. Here, it's a little different. We just went to a single group, students, and we asked them 2 questions. We asked them, do you smoke? Do you not smoke? Do your parents smoke? Do they not smoke? All right, but it was just a single group that we asked 2 questions. We didn't create the different groups. It was just one big group that we sort of broke down to ask questions. And that's the difference between when you call it a chi-squared test of independence and when you call it a chi-squared test of homogeneity. All right? Now, as far as carrying it out, like I said, you carry it out the same. The only thing that changes is how we write our null in our alternative hypothesis. When we're doing a chi-squared test of independence, the null changes to there is no relationship between parents smoking and students smoking. And then the alternative is pretty much the same exact thing, except we say there is a relationship. So it changes to there is no to there is a relationship. Between parents smoking and student smoking. All right. Another way to think about this is that the null is that they are independent, because we're saying there is no relationship between those two values. The alternative is saying that they are not independent, which is saying there is a relationship. And you can kind of see how this is the same thing as the homogeneous. With the homogeneous, we were saying, is it the same across all groups, or is it not the same? This is saying, is there no relationship? Is there no connection between this variable and this variable? Or is there a connection? So that's why the mechanics are exactly the same. It's just how you collected your data defines what you're actually testing. If you created the different groups and surveyed those different groups, you're doing a homogeneous test. If you just had one group and you asked questions and the data fell as it did, that's where you're testing for independence. But again, everything else is exactly the same. So alpha equals 0.05. You go to your calculator, you go to second x to the negative 1, brings up the matrix menu. You go to edit. I already entered the data in between the videos, so we've already got it there. You go to stat, tests, chi-squared test. Observed is A. Expected we'll just fill in automatically. All right, and then we get our results right there. All right. Again, degrees of freedom are 2. And that's coming from, we have 3 rows and 2 columns. So 3 minus 1 times 2 minus 1 is where that 2 is coming from. Again, our chi-squared statistic in this case is 37.57. Our p-value, which is found by finding the area above that. Notice there's an e to the negative 9 here. So we actually have 8 zeros, 1, 2, 3, 4, 5, 6, 7, 8. And then let's say 6959. All right, so a very, very tiny p-value. So based on this very, very tiny p-value, we reject the null and accept the alternative, which again is basically us saying they are not independent. All right, when we reject the null, we're basically saying, hey, those two things are not independent. All right. If we had failed to reject the null, it would have been there was not enough evidence to say that they were not independent. All right, it just wasn't. We didn't have enough data to say that they weren't. So that's kind of the difference there. All right. So again, you can see the mechanics are exactly the same. The only thing that changes is how you write your null and how you write your alternative. So when it comes to these problems, it's less about doing them, because doing them's pretty easy, and it's more just about reading them and making sure that you can pick out which type of test it is. So let's take a look at one here where we're trying to figure out which test it is. Is it independence? Is it homogeneity? So, do you use cocaine? I certainly hope not. Sample surveys on sensitive issues can give different results depending on how the question is asked. A University of Wisconsin study randomly divided 24 respondents into 3 groups. All participants were asked if they had ever used cocaine. One group of 800 was interviewed by phone. Another 800 people were asked in a one-on-one personal interview. The remaining 800 were allowed to make an anonymous written response. Are there statistically significant differences among these proportions? So, notice on this one that we divided the respondents into 3 groups. It was not as up here where we asked them 2 questions and then this is how the data fell out. We as the researchers created the 3 separate groups, and then we really only asked a single question. We didn't ask them, would you rather do this by phone, interview, or anonymous? We made that decision. We created those groups, and then we only asked a single question, have you used cocaine? So because we created the groups, we have multiple samples that we created, which means this is going to be a chi-squared test of homogeneity. Now, the other thing that makes this question a little tricky is they're giving it to us as percents. So that means we kind of need to create our own table here. All right, so if we were going to create our own table, we have phone, we have interview, and we have written. And then for each of those methods, they can either say yes or no. And then we have to use those percentages to figure out what our actual counts are. So each one, they told us there were 800. So for phone, if we do 800 times 21%, all right, that'll give us 168. Now, we could either do 800 times, what was it, 21%, so 79%. So we could do that and say, all right, this is going to be our nose, 800 times 79%. Or we could also have just recognized that those 2 numbers have to add up to 800. So this one's going to be 632. For the interview, 25% said yes. So 0.25 times 800 would give us 200. I have no idea why I did that on the calculator. That's embarrassing for me. And then the nose would be 600. And then 28% of 800 is going to be 224. All right, and again, we can just say that the other one is 576 because those are going to have to add up to 800. All right, once we have that, we're good to go as far as actually doing the problem. So let's write our null. Now, because this is a test for homogeneity, we have to make sure we're using the right null and alternative hypothesis. So we're not going to use the no relationship one. We're going to use the distribution of responses, which means the yes or the no's, is the same across all methods. So whether it's phone, interview, or written. And then the alternative would be the distribution of responses is not the same across all methods. All right. And really, that's the only thing that changes. Based on what test you're doing, you just have to make sure that you're writing your null and alternatives appropriately. Homogeneity, it's the distribution of responses the same across all methods. When it's independence, it is there is no relationship or there is a relationship. Everything else is the same. So our alpha is 0.05. If we go and put this into matrix A, we have 3 rows and 2 columns, so that's 3 by 2. It's already the right size. Just put in the numbers quick. 200, 600, 224, 576. All right, so all of those are in there. We go to stat tests. Chi-squared test, observed is A, B expected, keeping that all the same. Degrees of freedom is 2, all right. Same exact reason it was 2 up here. 3 minus 1, 2 minus 1 is giving us 2. Our chi-squared statistic is 10.62. So our chi-squared statistic is 10.62. Our p-value is 0.005. All right, that is under 5%. So because our p-value is under 5%, we reject the null and accept the alternative. All right, so what that's basically saying, the conclusion here is that the method matters. All right, the method that we use to ask people this question matters, which is what we would expect. Generally, the more anonymous something is, when you're talking about suspect behaviors or things that people aren't necessarily proud of, the more anonymous it is, the more honest people are going to be. All right, they have a much easier time being honest when it's just a written response than if it's over the phone or face to face or something like that. So by rejecting the null here, we are saying that it's not the same when you use phone, interview, and written. The method does matter. All right, so that's what the practice problems are really going to focus on, making sure that you can differentiate between homogeneous and independence, because the method is pretty easy and it's the same regardless. So really, if you can differentiate between the two, if you can read a problem and say, all right, this one's independence, this one is homogeneous, all you need to do at that point is just know how to write your null and alternative, because the rest of it is pretty easy from that point on. All right, so I hope these were helpful. There will be some practice sheets and some answers, so try those out, and best of luck. All right, have a great day.